Hello, hello, hello. Let's think a little bit more about adjunctions, and in particular, a particular kind of adjunction where we call a free-forgetful adjunction. So this is a typical situation where we have some category without much structure, such as the category of sets, and then some other category where we have more structure, such as the category of monoids. And one way to see this is that objects over here are of course a set X and a multiplication and a unit. So we could always forget about this structure in order to make something down here. So there is a functor going this way which forgets about the extra structure, right? But now let's say that we want to go the other way. So we want a way to turn a set into a monoid in the cheapest way possible. That is, we should make it a monoid, but we shouldn't make any other extra choices. So I want f of x to be a monoid, and I want it to satisfy no other equations. So in some sense, it should be the smallest monoid that contains x, right? And you could try to formulate this naively, but a very nice way to do it is to say that this should be the left adjoint of the forgetful functor. So let's see why that is the case. What does that mean? Well, it means that monoid morphisms out of fx to some monoid A should be the same thing as functions from x to forget of this, which is just A, right? So saying that we can get a monoid morphism, so that's a structure preserving morphism, out of fx just by saying what's happening to the generators. So we call x the generators of this thing, and we call this the free monoid on x. And why is it on x? Why is it called generators? Well, if you take A here itself to be f of x and this to be the identity, the standard trick, then you see that you do have a way to embed x into fx, right, as a function. So it contains x, and it's the smallest thing that's a monoid and does so. And smallest in the sense that you always get the monomorphism to every other thing that contains x, right? So that's an elegant way to state what it means to be a free monoid. Let's say that you have a left adjoint, but then it's not enough to state it, we also need to construct it, right? And if you think a little bit, then you see that if you take the carrier of fx to be lists of elements of x, then you can take monoid multiplication to be concatenation, and you can take the empty list to be the unit. Then this is certainly going to be associative and satisfy all the laws that we want. And furthermore, this is really the smallest amount of information that we need, because we need to be able to represent arbitrary multiplications like this, right? So we certainly need to know a list of the elements occurring in this multiplication, and by making it a list, we are saying that all the different bracketings doesn't actually matter, right? They are all going to be flattened out. The other alternative would have been to make it a tree, but then it wouldn't have been associative. So that's the idea behind it, but there's a lot of creativity in coming up with that, right? It's not something you can really calculate, which is part of what makes it fun. So let's see if we can prove that this definition of the free monoid actually is the free monoid. So here I've already defined it. So I'm saying that the carrier are lists, multiplication is concatenation, unit is the empty list, and then all these laws just follows from the standard laws of concatenation. So it's associative, left identity, and it commutes with map, etc. Right? So basically the F map is the map of lists. Okay, so now let's see if we can show that this is an adjunction. So the nice thing is that after we've had this idea of making this a list, then asking ourselves if it's an adjunction already tells us lots of nice things that we can prove, and that's going to be useful for us. So we're kind of guided by this higher structure. So let's see what we should prove. Okay, so we need these maps between the Hom sets, right? So here we get given a monoid morphism from lists of x into B, and we have to create a function from x into the carrier of B. So if I have such an H, and I want a function from x, and let's take an x as an argument. Okay, and I want something in the carrier of B. And what do I have? I have H. So H has an underlying function, which if you give it a list, gives you a B. So we don't have a list, but we have one element. So we can, of course, turn that into a singleton list, right? So here we're saying that we're seeing one element as a degenerate list in a way. Right? Okay, going the other way, if I have a function from x into the carrier of B, I want to make a monoid morphism from lists of x into B. So let's see. That means I need an underlying function. And what's the idea here? Well, I should take this list and I should treat it as a formal multiplication, right? So if it's a 2-element list, then I should multiply these elements together. If it's a 5-element list, I should multiply them all together. So I think I'm going to define this as a separate fold function. So I have a set x and a monoid B, and if I have a way to turn individual elements into monoid elements, and if I then have a list of x's, then I can turn them all into monoid elements. That's my claim. Okay, let's see how I would do it. A pattern match on the list, of course. If it's empty, then this represents the empty multiplication. That should be the unit of the monoid. And otherwise, okay, let's open B. Okay, otherwise I can multiply the first element, that's x, but that lives in x, so I interpret it as a monoid element. I can do that with single things, so I multiply that with the rest. Right, so this means it's g of the first one times g of the second one times g of the third one until you get down to the empty list, and then it's times unit, which does nothing, right? So that's going to be my underlying function. Okay, and now we get told interesting things to prove about this function, right? Which you might not think of otherwise. So here, that it preserves the unit is not very interesting, but it's easy to prove. Here, if I get given an x and y's, then this is asking me to prove something interesting about how this fold function interacts with concatenation, right? So it's not just commuting with it, it's doing something more interesting here. So, right, let's open B so it's easier to read this goal. Except for that to work, I just bring B into scope. Okay. Right. So here I can pattern match on the x's to make some progress. Right. And here I've lost one on B. So this looks like identity, right? Is it right? No. So where's the other one? It's sim of that, right? here, what do I need? Well, this looks like a recursive call, right? So let's do that. Okay, but that's inside the fx times blank, so let's con with that. And that's a good start, but the end doesn't look quite right, so use that as a first step with a trans. And then let's see what remains to be done. This looks like an associativity problem. Right. Okay, and here, what do we have to prove? So this is the round trips now. Right, so here's another interesting thing we should prove, right? Which says that if we do the from, which we define to be the fold, and instantiate it in a certain way, then we recover the H, which was the monomorphism we started from. So again, this is an interesting fact that we are just told that we should prove by trying to prove this adjunction. Okay, so I think I'm going to talk about X and B, so I'm going to bring this into scope first. And then I'm going to see. So this is an equation between monoid morphisms, right? So we have a way to prove that they are equal. Just looking at the underlying things, and I'm talking about fold. And now this is an equation of functions, so we have a way of proving that they are equal. Because we don't need that, because the next thing we're going to do now is to make this into a lemma. Right. So something like this, but I'm going to first of all rename this, and then maybe this will work. Let's try it. Okay. Is it fit for purpose? Yes. Okay, so here we need that fun H apply to unit is unit. Okay, but H is a monoid morphism from this free monoid to B, so it's a monoid morphism, so it preserves the unit. Right. Okay, so that looks right, except that it's the wrong way around. Okay, and what about this one? Let's open B so we can see what's going on. Okay, this again looks like a recursive call, right? My axis, and then it's inside this. So do a con of this. Okay, and then this thing here doesn't look quite right either, so let's see if we can fix that for the second step. Okay, so this looks like some interaction of H and multiplication. Right? So we know that H preserves multiplication. So we give it two lists. Well, here's a singleton list, and here's another list. Axis. Okay. That looks right, but it's the wrong way around. Okay, so that was very similar to what we did up here, by the way, right? We did the same kind of steps. So That's not entirely by accident, but let's ignore that for now. Okay, so here what do we need? We get given a k, and we want to show this equation holds. So let's do it in function extensionality. Okay, and here we can again open the monoid B so we see what's going on. Except we don't have B in scope. Okay, so it's another instance of an identity. This time it's right, I hope. Yes. Okay, so we've shown the inverses, and we kind of did it by just looking at what's in front of us and proving that, right? But the point was that we didn't have to come up with this lemma ourselves. It was just we were told by the adjunction that this is an interesting fact that you should prove about fold. So it's nice not having to think. We did all the thinking when we came up with the free monoid and with to and from, right? But okay, let's see if we can do the last bit, just the naturality. If we're lucky, this is easy, and we are lucky. Right, so that was nothing interesting. All the interesting things happened up here. So now we know that this is a good definition of the free monoid. It's not something that just looks kind of right. It's right because it has the strong universal property of being an adjunction, which tells you lots of things about it as well, which is nice. So this is one way of freely creating structure, right? By saying it's the left adjoint of a forgetful thing. This is often very powerful, partly because it gets you something for free, and also because you know what interesting facts to prove about it just by stating it as an adjunction problem.